Finding a star 4, Red Ascension and Ecliptic Plane. I am Dr. Midway. I am a physicist and I'm learning astronomy. This is the last video of the 4-video series on how to find a star by reading its coordinates. Previously, we learned red ascension is the number of hours behind the Sun on March 21st, vernal equinox. We use the Ceres as example. Ceres is about 7 hours behind the Sun. But the Egyptians observed the Sun and the Ceres rise at the same time at the end of June or early July. Why is that? Still, I remind you, the celestial sphere is moving from right to left. And we're going to use a static picture to make explanation easier. At vernal equinox, the Sun is at 0 declination and 0 red ascension. The next day, after 24 hours, all of the stars on celestial sphere come back to the exact position. They are like rule followers, on time every day. But our star, the Sun, doesn't come back to the same position. It is sneaking around. After one day, it comes to a position a little bit above the 0 declination and a little bit larger red ascension, not 0 anymore. It does the same thing again after another day, moves a bit more above and a bit more to the right. It keeps doing that every day. If we trace its relative motion, we will get a green line on the celestial sphere. It's called ecliptic or ecliptic plane. In modern time, the definition is orbital plane of Earth around the Sun. But in ancient time, people doesn't know Earth moving around the Sun. So the Sun's movement around the celestial sphere over the course of a year traces out a path along the ecliptic against the background stars. That's how they find it. They're pretty smart. Now let's see how the Sun moves along the ecliptic on celestial sphere. From vernal equinox, after 1 year, the Sun comes back to 0 declination and 0 red ascension. That's 12 months, and the red ascension is labeled by 24 hours. 24 hours divided by 12 months. Then each month, the red ascension changes by 2 hours. On vernal equinox, the Sun is at 0 declination and 0 red ascension. After 1 month, in April, the Sun moves to 2 hours red ascension. In May, red ascension of the Sun becomes 4 hours. On June 21st, 6-hour red ascension. When Sun's red ascension increases every day to the right, its declination also moves north every single day. Now it reaches its highest point, 23.44 degrees, at the Tropic of Cancer. It's the summer solstice. The longest day. After that, the Sun's red ascension keeps going to the right by 2 hours per month, but its declination decreases, start to move south. On September 21st, in the fall equinox, the red ascension becomes 12 hours, and the declination reaches celestial equator. Then the declination becomes negative, keep moving south from here. Keep moving south until December 21st, the winter solstice. It reaches Tropic of Capricorn at minus 23.44 degrees. Now the red ascension is 18 hours, and the declination changes direction, return to north. On March 21st, after 1 year, the Sun is back to 0 red ascension and 0 declination. Now let's take a look at a Sun motion simulator. The latitude is 45 degrees, and the time is noon, and it's in March 21st. And now look at the celestial sphere, South Pole, North Celestial Pole, and the blue line is red ascension, 0-hour red ascension. And there's another blue line underneath the yellow. That's the zero declination. The yellow line is the sun's declination. It's the sun's daily path. Now let's start the simulation. You will see the sun moving. Gradually, the yellow line, separated from the zero declination, is moving north. Let's speed up. Now let's slow down a little bit so you can see how the right ascension changed. The blue line is zero right ascension. See, the sun has moved away from the zero right ascension. Speed up again. Let's make it super fast. Move to June, close to the summer solstice. Now the declination at its highest point. Now it's going back to the south, the yellow line. Let's fast forward again. Close to the fall equinox. See the yellow line? Now it's very close to the equator. Now it's past the equator. Keep going south. Let me slow it down so you can see right ascension. From 0 hour right ascension, the blue line, now the sun is at about 12 hours. It's opposite. Back to the fast speed and move forward to the winter solstice. December 18th, 19th, 20th, 21st. Now it reaches the Tropic of Capricorn, going back north. Fast forward back to the equator, the vernal equinox, March 21st. Let's stop there at the noon time. Now you can see it's back to the zero right ascension and the zero declination. This super good simulator is made by University of Nebraska. Unfortunately, Sheldon doesn't like Nebraska.
But Penny, you're from Nebraska, correct?
Born and raised.
Let's look at Sirius. At the vernal equinox, it's 7 hours behind the sun. In April, the right ascension of Sirius doesn't change, but the sun has moved from 0 right ascension to 2 hours. Now Sirius becomes 5 hours behind the sun. Each month, the sun moves by 2 hours. So in May, Sirius becomes 3 hours behind the sun. In June, only 1 hour behind the sun. And sometime at the end of June or early July, Sirius will rise with the sun at the same time. So the Egyptians can observe the heliacal rising. In June 21st, Sirius becomes 1 hour ahead, and this pattern just keeps going until March the next year. Remember, a few hours behind the sun is a good time to stargaze Sirius, such as January, February, March, and April. Look for the winter triangle. Now let's look at the star Vega. In last video, we learned in March, Vega is 18 hours behind the sun and equivalent to 6 hours ahead of the sun. And we can only see it early in the dawn before sunrise. In April, it becomes 16 hours behind the sun. And with the same pattern in July, it becomes 10 hours behind the sun. Then you can try find it in the evening. And September is a very good time to look for Vega and the summer triangle. This is the end of this video series on how to read celestial equatorial coordinates. If you like this video, please subscribe, like, comment. Thanks for watching.